Give me a sec. I need to open mine.
You can just cut this whole part out.
Yeah. You guys ready?
Should we mute
Yeah.
ourselves like when we're not talking so there's no background noise?
Yeah.
Okay.
Actually, yeah. Okay, ready. Ready? Hey guys, we're group 6, and our word is partitions of a finite set by me, Shino Kumar, and David Gonzalez. So what is a partition of a finite set? A finite set is a set that contains a countable number of elements. For example, a set containing 2, 3, 4, and 5. A partition of a finite set is a grouping of its elements into non-empty subsets in such a way that every element is included in exactly one subset. Every partition must be a subspace of the set. For example, let S be the set 2, 3, 4, 5, 6, and 7. One possible partition of S would be P, which contains 2, 4, 6, and 3, 5, 7. What is not a partition of a finite set? A partition of a finite set is defined to not have an empty subset. So for example, let S be a set and P be a partition of S. If S contains 2, 3, 4, 5, 6, and 7, P cannot contain an empty subset. A partition of a finite set also can't include numbers that aren't in the set. For example, let S be 1, the set containing 1, 3, and 5, and P be the set containing 1, 3, 5, and 2. Here the element 2 is not in the set S, therefore P is not a partition of S, since P cannot have more elements than S. Some fun facts about partitions. The empty set 0 has exactly one partition, which is itself, and the set 1, 2, 3 has exactly 5 partitions, which are 1, 2, and 3, 1, 2, and 3 together, 1, 2, and then 3, 1, 2, and 3, 2, and then 1 and 3. The number of partitions that we can have is based on the Bell's triangle, which is made of Bell numbers, where n is equal to the number of elements in a set. If we have one element, we will have one partition. If we have two elements, we have two partitions, and so on. The number at the end is the number of partitions.
And here in this slide, we'll be proving the Bell's triangle. In each row, it shows the number of elements in the set and the number of partitions. For example, in the second row, it shows the set that contains the elements 1 and 2, and it has 2 as the number of partitions. And as you go down, the number is increasing. For example, such on the fourth row, it has the elements 1, 2, 3, and 4. And the number of partitions increases to 15, which is much bigger when compared to the one before that. And it goes on and on as the number of elements in the set grows. Our research question: how many partitions of a set will we have if some number of the elements in the set are allowed to go in multiple partitions? Assume that only one element can do that to start, and see if a pattern emerges that the number of flexible elements increases. Can you create a formula? Does the formula hold up in general for any size set, or is it completely different based on both the size of the set and the number of flexible elements? Here we have an example showing the flexible elements. So and n equals 1, only 1 is allowed in multiple partitions, and 1 being the flexible element. And it has 2 being the number of possible partitions. In the next row, we have 1 and 2 being the elements, the flexible elements, and it increases to 3 partitions. And after that, we have 1, 2, and 3 being the flexible elements, and we have 5 partitions. And as shown in the previous slide showing the bell charts, it would keep increasing. And by prediction, if we have 4 elements, n equals 4 would have to have a total of 10 possible partitions in order to be consistent with the chart shown before. Can we create a formula based on the amount of flexible elements in a set? The sequence that we created is 2, 3, 5, 10. There is not a formula that is consistent with the sequence. However, if all elements are allowed to be repeated in multiple partitions, we have the formula which gives us the number of partitions, and we have the formula right there below.
So for our conjecture, we tried to see if there was a relationship with partitions and combinations. And we found a formula for Bell numbers. The Bell numbers tells us how many partitions are in a finite set if all elements are allowed to be in multiple partitions. If we search our previous sequence with inflexible elements on the online encyclopedia of integer sequences, what will we get? So by inputting the sequence 2, 3, 5, 10 into the OES, we actually see this concept of Dedekind numbers, which is really interesting in the next slide. If you would like to read the rest of this, that's up to you. So here's the information from the previous slide. We have this graph of information, and what's interesting about it is that these sets are also in subsets as well, and they are partitioned. And also what we can see is that it creates a triangular shape, which aligns with our previous slides about Bell numbers, which are concepts that have all of the elements, but this sequence only has the flexible amount of elements. So we can see that relation here. And so these are our references. Thank you so much for listening to our presentation, and I hope that you guys have a wonderful winter break.